I cannot share once. I share my screen. I think we're in this part already. Please check if this is the last. I think this is where we ended. Finding solutions of differential equations using Laplace transformation. So we did transform the derivatives of functions. In this case, this would be the derivatives that I'm referring to. That way we can find the solution of this given differential equation. So I think this is the last part. We ended last meeting. So for the day, we will continue with the rest of the properties. And if we have time, we will go through the problem set that were given to you to check. So whether you can process them based on what was taught to you in your advanced engineering mathematics. So our fifth and sixth properties here on this slide would be the initial value theorem and the final value theorem. Now, what is good about these two properties is it's not anymore important that you know how to invert your given function, or that, let's say, for example, you're given a function of s and then there's a need for you to determine the function of t and substitute the corresponding value of t, which is 0 for initial value, and t, which is infinity, for final value, for you to be able to determine the value of the function. Let's say, find the initial value of the function. So that would need the f of t expression, and then you substitute t equal to 0 to the t's. If you are asked to determine the final value of the function, that would require you to substitute infinity to all the t's in your function of t. Using these two theorems does not require you to invert the given function of s. That way, you will have to process the given value of the function as a function of t. In here, in these two theorems, you directly use the function of s that is provided, you multiply it with the s, and these two theorems differ only in the value of the s in which your particular product of s and function of s is approaching to. So if we determine the initial value of the function, we substitute s equal to infinity, or we evaluate this limit as s approaches infinity. The limit is the product of s and your given function of s. That's for the initial value theorem. And for this theorem class, we don't have any limitation. So meaning whatever is the corresponding f of s expression, just multiply it with the s and evaluate the limit as s approaches infinity. On the other hand, when you're provided with the function of s and you want to determine the final value of the function, you are to substitute s equal to 0, or you are to evaluate the limit of the product of s and the function of s as s approaches 0. In this particular theorem class, there is a limitation, meaning you can only apply this particular expression, or shall I say this particular expression is only applicable if the function of t exists as t approaches infinity. And the very easy way of determining whether the f of t exists as t approaches infinity is that you check first prior to evaluating the limit of s times the function of s as s approaches infinity, if rather the product of these two is not equal to infinity for all real values of s greater than 0. What does this mean? Before you evaluate this class, you check first if the value of s times the function of s will be not equal to infinity if you substitute any s value, real value of s, greater than 0. So meaning you are not allowed to substitute a real value for s which is negative. As long as s is greater than 0 in the original s times function of s expression and the answer to the product is not equal to infinity, then you can proceed to evaluating the limit of such particular expression. So there is a need for you to check this first. If this is true, for s times function of s being not equal to infinity, then you can proceed to determining the final value of your function, and that is the value of the function as t approaching infinity using this alternative formula, which does not require you to invert the original function of s. Okay, for you to understand that better, there's a sample problem here. So we have the limit of s times the function of s. If we are to determine the initial value of the theorem, we will evaluate it as s approaches infinity, which is also equivalent to determining the limit of your y of t as t approaches 0. That is your initial value of the function. Now, let me annotate for you to understand. So in this case, so you have to evaluate your s times your y of s. And that corresponding value would be, I'll just write it here, your limit of s times y of s as s approaches infinity would be equal to, so you have s, based on our formula, the limit of s, oh sorry class, the limit of s times, we copy everything here. So you have 4s plus 2, and you have s times s plus 1, s plus 2, and s plus 3. This is as s approaches infinity. So we cancel the s, and then we substitute infinity here. So you will have the limit of 4s plus 2 over. So you were taught in your differential calculus that whenever you evaluate the limit of an expression in which the value of the variable or the value in which your variable is approaching to is infinity, there's a need for you to expand the denominator if it is having several factors on it. So I'd like to expand the product of these two first. So that would be s squared plus 3s plus 2, and that would be multiplied to s plus 3. And then again, I'll place here s approaching infinity. So this would be again equal to the limit of, so you have 4s plus 2. Then we expand this again. So that would give us an s cubed. And this one would be a 3s squared and another 3s squared. So that would be a 6s squared. Then as we have here a 2s and a 9s, that will be an 11s, and you have here a 6. So this is the third degree polynomial equivalent to the quantity s plus 1, s plus 2, and s plus 3. And then as a review of what you have in your differential calculus, you divide both the numerator and the denominator by the variable in the denominator having the highest exponent. Okay, so in that case, there's a need for you to divide this entire expression here by s cubed. The same would be true for what's in the numerator. So the result of that would be your denominator will have, I'll just write it here. So your denominator would be, in this case, an s cube, and an over s cube would be 1. And the rest of this expression, which will be divided by s cubed. Once s is infinity would be a 0. So I'll just place here 0 because anything divided by infinity will be a 0. In your numerator, you will have 0 also. So 4 over s squared plus 2 over s cubed would be 0 for both terms. So the answer, then, the answer for this, as you can see here, is 0. Because 0 divided by 1 is 0. So this is said to be the initial value of the function evaluated or determined using the initial value theorem. Without the initial value theorem class, you will need to invert this expression. And if your recollection of your Laplace transformation in advanced math is still fresh, this will be a tedious process because you will use the method of partial fractions just for you to be able to get the y of t from this particular y of s, and then substitute t equal to 0 for that. Now, with the initial value theorem, you directly determine the initial value of the function by evaluating this one, this limit. Okay? As for the final value theorem, you just simply have to check whether the product of s and your y of s will be not equal to infinity when you substitute a value of s which is greater than 0, or real values of s greater than 0. So for me not to repeat again, you will actually be taking the same product that I have here. So the resulting expression would be this one still. Okay? And if this is your resulting expression, final value theorem checks first whether if I substitute s here greater than 0, my answer would be not equal to infinity. Of course, the answer would be true because if I substitute any value here not equal to 0 but greater than 0, I will have a real value, which is not infinity. So I can then proceed to using the final value theorem, which is just but the same expression here, but I will evaluate as s approaches 0. So in this case, class, I will simply substitute s equal to 0 here. So my numerator will be left with 2 and my denominator will be left with 6. So 2 over 6 will be 1/3. So that's the thing that you are seeing here. The final value of the function, sorry for that. The final value of the function using the final value theorem is 1/3. Okay? Any question? So this would be the initial and the final value of the function, the given function, which is this, using the theorems that was discussed in the previous page or previous slide. So easy to follow. Just check first whether if you're going to use the final value theorem, your s times your given function will not have a value which is equal to infinity if you substitute an s which is greater than 0. For the initial value theorem, there's nothing for you to check because it has no limitation, meaning it's applicable for all scenarios. Only the final value theorems needs checking. Okay? Now, I will proceed if there are no more questions here. Okay, and then that would be our next. So in here, I place the special term offset. When you actually determine the final value of the function, you are also determining what we call as the offset, or how much is the ultimate value of the function or the ultimate steady state value of the function differ from the set point or from its original value, and that is still offset. This means, class, that whenever a problem is asking for you to determine the offset, it's just like it's asking for you the final value of the function. So just get the final value using the final value theorem as written here. Now, this example 3 already introduces what we call as the step function, which of course will have what we call as a step response, or an input, which is said to be a step input, and as such, it will produce what we call a step response. So in the original expression here, class, by the way, this original expression came from just to give you an idea, but we will still discuss this later, came from the transfer function of a function. And what is the transfer function of a function? That would be the Laplace transform of the output divided by the Laplace transform of the input. So from this original expression, actually, we are determining the step response when your x of s, in this case, your x of s is equal to a over s. Don't worry for now, why is it a over s? Because I'll be discussing it specifically in responses. So your original y of s over x of s now is changed into, so from this original expression, you have this, wherein your x of s was cross multiplied here on the right side, or transferred by multiplication on the right side. So you may wonder, what is this, miss? What is this expression? This is the transfer function. This is the transfer function multiplied by the x of s. That is the Laplace transform of the input. Now, let me erase this first. So in that case, now, the transfer function times your x of s, which was cross multiplied now, which is a over s, will give you this one. So if you will determine the offset, what is the offset? So you can see it's the limit of s times the y of s as s approaches 0. So what we do, you first determine the sy of s. So this is it. Then you check if I substitute any value of s greater than 0 here, will this particular product be not equal to infinity? Of course, the answer is yes. So meaning you can go straight to using what we call as the final value theorem, which is the limit of s times the y of s as s approaches infinity. If you substitute s here equal to 0, your answer would be an A. So we say that the offset or the steady state error is equal to A. Or your offset, which is equal to how much is your new steady state value deviating from your original steady state value, is A, because it's the value that you're getting here. But this is just but an introduction, or will give you more or less an overview of what we will be discussing in the next weeks. But this is just to illustrate to you the concept of the offset. But we will still be discussing this in detail later on. Okay, so let me clear the drawings here now. Now we proceed to the next property. So the next properties, the 7 and the 8 properties, are actually in your advanced math referred to as the first shifting property and the second shifting property. What is the first shifting property? It happens when your function, your original function, is multiplied to an exponential function. So what happens is all the s in the function of s resulting from the Laplace of the original function will be shifted by subtracting from it the a. So the a that appears here in the argument of your exponential function. So s minus a, so that would be s plus a. What does this mean? All the function of s in the original transform, or all the s rather in the original transform of the function of t, will be converted to s plus a, or you just simply change the s to s plus a. Now, this is the first shifting property, and this was taught to you already in your advanced math. This one is the second shifting property. When does this happen? This was also discussed in advanced math. This is equivalent to, let me annotate, taking the Laplace of a function in which the t has been shifted. So it's the time that was shifted. T minus a, u of t minus a. This is the way it's written in advanced math. We call it here, or this is referred to as the second shifting property in advanced math. So it's not that the function Laplace transformation that is being shifted, but this time the t first in that particular function is shifted already. Now, let me explain this. What's the difference between the two? Sa first shifting property, ang S mo ang nag-shift, meaning ginkwa mo na nga daan ang Laplace transform sang function, kag dason din shift mo lang ang tanan nga A nga nag-appear dira by subtracting from it the A. In the second shifting property, it's not the transform that has been shifted, but it's the time of the function, the time or the t variable in the function that was initially shifted. So that is why it's called the time translation. It's the time there that has been first translated. So what is its effect in its transformation? Its effect would be you have to get the Laplace transform first of the function without the time translation and then get the Laplace transform of that. Get the function of S from the f of t without the translation, then get the Laplace transform of that. That would be your function of S here. Then what you do after that is you multiply the f of S by e raised to minus st. Or whatever is this. By the way, class, this t here, the capital T here, is actually the A that I have written here. In advanced math, this is written as A. That is why I wrote it as A here. But in process control, it's written as T, capital letter T. So this is just the A that I wrote in here. And this is the same A that appears here. This one, this T, and this T in here. Okay? In pure math, this capital T is the A that you are seeing here. Okay? So in advanced math, we call this the second shifting property. This one we call the first shifting property. Now, in Laplace, in process control, we call this one the time delay or dead time, or this is known as the translation of the function or time translation. It is the function that was first translated or the time in that particular function was translated because of this one. Okay? Or a unit, you have here a unit step function that has been shifted. So it could be also class that the shifting here is not similar to this one. I'll give you specific examples later. In here, this is very easy because this is just the ordinary first shifting property. We just refer it in here to as the complex translation, or we call it that the transform, specifically the Laplace transform, has been translated, or that's translation of the transform. Okay, now this particular, I think, I'm not sure if I have given this in the problem set, but we will check later on if you have a similar expression to this in the problem set that you will process. But nonetheless, this is how it's called here in process control. Okay, this is how it's called in advanced math. This is how it's referred to in here in process control. Only the terms change, but how you process them is just the same as you do in advanced math. Now, let me just finish the properties, then we will go to specific examples. Then this would be the last two of the 10 properties. And this discusses or introduces the Laplace transform of two unique functions. So if you recall, I have discussed in part what is a unit step function there as an example of the principle of the offset. Another form of function that is common here in process control, aside from the unit step function, is the pulse and the unit impulse. The pulse function is a function in which doesn't have a value for t less than 0, so it's equal to 0. And for t greater than h, it will not also have any value. It will only have a value which is 1 over h on the interval 0 to h. Now, for you to understand this better, I'll go straight to the next slide because it's there. Its graph is in here. You see this? So this is actually a pulse. That's the pulse that was described to you on the previous page. I'll write it here. So it's like saying that at time less than 0, the value doesn't have any value. That function rather does not have any value. It's 0. There's nothing here. At time less than 0, I don't see anything here. Its value is 1 over h on the time interval 0 to h. Where am I getting this? You see this? This is h and this is 0. So on the time interval 0 to h, the value of the function is 1 over h. You see this? Meaning it's constant at a value of 1 over h when we speak of a time interval starting from 0 to h. Okay, so its value is 1 over h. What about if the time is greater than h? Greater than h time is this, beyond h, and it still doesn't have any value because you see here nothing. There's nothing here. So this is the pulse that you have seen in the previous slide. Okay, this is the graph of the pulse that you have seen on the previous page. Now, if I go back to that page, let me just erase. Okay, so this is the way, this one is written this way, and that represents a pulse. Now, how do we get the Laplace transform of the pulse? Okay, this one, how do you get the Laplace transform of this particular function? So it will be using the previous property, which is the time translation, or we say that the function was translated, or the time variable in your function was translated. So how will you process this? In your advanced math, this should be processed by this one. This is how you should process it. The value of this, which is 0, you will multiply it by this one. Whatever value you see here. Since this is 0, you will simply multiply it by u of t minus 0. Now, there's a question, Miss, what if this is not 0, Miss? Let's say, for example, mathematically only, not for the pulse, because the pulse will always have this as 0 and this is 0. Let's say, Miss, this is not 0, this is 1. So this would be u of t minus 1, if this is 1. Let's say, Miss, this one is not 0. Let's say, for example, this is 10. So this would be 10 times u of t minus 1. So the function value here, the function value depends on what is written here. If this is 0, you write 0 here. If this is t, you will write t here. If this is t plus 1, you will write here t plus 1. If this is sine of t, this will also be sine of t. You will always multiply it to u of t minus whatever is the constant that appears in here. But again, I'm going back in the past because it's what we're talking about now. But in pure math, whatever is the function here, you copy. And whatever is the constant here, that would be the constant that should be subtracted from the u of t expression here. Or that would be the shifting of your unit step function. That will be multiplied to this function value here. Now, what happens to the other values here? So since the function assumes these 3 value, you will add product. So you will have 1 over h, and again, you will have the u. But this time, class, you see 2 n's in the interval. This only has 1, while this one has 2. So what will happen? You write here u of t minus 0 minus u of t minus h. Question, what if, Miss, this is 2? What if this is 2? This should also be 2. What if, Miss, if this is 7? Then this should be also 7. So the shifting that will occur in the unit step function would be exactly the same as the interval that you are seeing here on the particular value of the function in which you are multiplying it to. So you notice that it's always function multiplied to the u of the expression. Function times the u of the expression. Is this always a minus, miss? This is always a minus. By procedure, this is minus. Is this always, miss, plus? This is always plus because these are the three values in which your function assumes. If this is 25, you change 1 over h to 25. Now again, we have here a 0 for the pulse. And then we will multiply it to u of, just like what we have done here. You have 0 in here, we have h. So this would be multiplied to u of t minus h. Now, anything multiplied to 0 will be a 0, right? So then you will have the middle term remaining. So I will simplify the middle term to be 1 over h u of t. And then this 1 over h should also be distributed on the second term. So I will have here minus 1 of h, u of t minus h. Now, what is, now you will, let's say this is your function already. This is your function of t. This is your function of t coming from this. Now, what if now the goal is to determine the function of s? What if it's the function of s? So you will get the Laplace transform of these two expressions. Now, the Laplace transform of the unit step function was already given to you last meeting, and that's equivalent to 1 over s. So it's like you will have 1 over h, which is a constant because it represents the magnitude, times 1 over s, the Laplace transform of this. For this one, you have a minus, and you have here a minus, and this is also a constant, so you have 1 over h. And this one, from advanced math, the Laplace transform of a u of t minus a constant is automatically class e raised to negative that constant times h. Now, this is the exact thing that you are seeing here. Okay. Okay. Do you get it? So you just factored out the 1 over h, and then you have here, by the way, I forgot to place here the s. Automatic class, this is the units, the Laplace transform of your u of t minus h. So, and e raised to hs. So if this is a 10, this should be 10s over s. So what was done is you have the factoring of 1 over h in here, and then the s also that appears in the denominator, and you have this 1 and e raised to minus hs. This is the Laplace transform of a pulse function, or better yet, this one. Now, since it's already pre-derived for you, class, what if this pulse is 10? You just change the 1 over h and make it 10. And let's say, for example, this one is 7. So you change this to 7s, and this would be 7 as well. So hindi na mag-tag-isa-isa ulit na kwaon ang Laplace transform this way, because this was taught to you already and it was derived for you. So automatic, you just change whatever is the magnitude of the pulse here. This one is changed correspondingly. And this h here is this h that appears. So if this is a 2, this should be a 2. If this is 20, this entire thing is 20, this should also be 20. That's automatic. No need for you to go through this. But if you want to practice to go through the process of coming up with the Laplace transform of a particular pulse, then you can do so. But this is how it was derived. Okay? Just give me class. Wait, class.
Yes, I'm here. I'm trying to find what should I play. Yes,
Okay, wait, class. Wait lang. Do you have any questions so far in this part?
Morning, Miss.
Yes.
Miss,
Uh-uh.
Miss, lang curious lang ko bala misaw. Ang greater or lesser equal sign is wala ka-affect Miss sa pag-translate Miss sa unit and form.
Sa sini? Sa sini nga form?
Miss.
Amo gini siya ya ang
Miss.
pangsulata this one Sarah is really less than 0 based on the I will just draw the pulse here. This is your pulse. It has a value of 1 over h on the interval 0 to h. So it would really have a big impact if you change this to greater than 0 because it has to be less than 0, meaning your pulse will not have any value for time which is negative. Your pulse will only have a value of 1 over h for time which starts at 0 time to h time. And again, your pulse will not have any value. You can see here it's a 0 for time greater than h. So as to the less than and the greater than here, and all the less than in here, it should be written that way. Otherwise, the pulse will not be represented in this form. Actually, this graphical representation is based on this. If this is misrepresented, you will not come up with a pulse that is that of a rectangle. It's represented in the form of a rectangle of magnitude 1 over h, and this is magnitude and duration of until h, or a time duration until h time, starting always at time equal to 0. Did I answer that question?
Yes, Miss, thank you.
Okay. Any more questions? Okay, so there are no more questions regarding the pulse. Now, I will erase everything here because I need to discuss the impulse, the unit impulse. The unit impulse is just a, shall I say, an idealized mathematical representation of a pulse. But when do you apply the impulse to when do you apply, yes, the impulse function to a pulse? You only apply it to a pulse when the time duration is very short, like 1/4 of a second, 1/8 of a second. So it's a very short amount of time that more or less you can say that nothing happened, or it's something that is very negligible. So when the pulse occurred for a very small amount of time, less than a second, then you may represent it as an idealized mathematical representation of the impulse function. So pwede mo siya ma-represent as an impulse. But again, in real life or in real industry application, there is no such thing as an impulse representation. Ginausar lang na siya para magsimple ang kabuhi isang nagasolve nga hindi siya mabudayan kung ma-solve pa siya sang impulse, sang pulse gidya nga Laplace transform. Because if it's an impulse function, automatically its Laplace transform is 1. So let's say, for example, the impulse function has a magnitude of 25. So you will not have to go through this. You just simply write here automatically 25. Because 25 times 1 is 25. So whenever you have a disturbance later on that will happen for a split of a second and you are asked to represent it ideally or simplify it ideally by using an impulse function, you may do so. So this is it. So this is the Laplace transform of a unit impulse function. So if it's not 1 in terms of magnitude, then automatically whatever that magnitude is, that would be the constant that should be written here. But again, the unit impulse function is just a mathematical idealization of the pulse whenever the pulse occurs in a very short amount of time. Okay, you can also read further on that particular explanation in Kauhanor, in our textbook, which I have shared already to you in Canvas. Now, here you could see that you have the original pulse here. So this would be more or less a graphical explanation of what is happening when you turn a pulse to an impulse. So when h approaches 0, meaning in our language, class E, ano mo ni siya bala ipabalik mo di siya pagamayon mo siya, ang iya value, do 0 na lang. Your function is behaving more or less a Dirac delta function, or that's the impulse function. And automatically, the Laplace of such is equal to 1. So when you get the function of S for this particular, this is the representation of our pulse, 1 over h. This is its magnitude. That's the function value. And automatically, this is the exponential function that is being multiplied to this particular magnitude. You will integrate it from 0 to h. So you will have to integrate this expression. Upon integration, this will be the answer that you will be getting. So if h is equal to 1, you will have a rectangular pulse input. If this h is equal to 1, then you will have a rectangular pulse input. This is 1 over 1 and this is 1. Actually, kung tanawon mo, 1 over 1 for this and this is 1. So that would be more of a square na. Kaya pariho iyang ini kag ini. So square na siya pariho na iyang dimension. Again, the Dirac delta or the impulse function is just a mathematical idealization of the pulse that occurs for a very short amount of time. Any question here? None? Okay. Okay, this is the end for now. So we'll go to, we still have 15 minutes. I'll stop sharing here. We'll go to your dashboard and we'll see what's in your problem set. Let me share again.
Mommy, when I tried to do the thing that teacher went up to play, it won't let me click even I'm clicking it.
So what did the teacher say?
Well, I tried to click one more time, but it didn't work.
So what did she say? What will you do?
I had to play that thing that she showed us in her screen. She said you have to play this thing on my screen. So I tried to go over to it, and when I click it, it didn't let me play. I tried it a lot of times to click it.
Okay, you take your snacks. We'll check it later. Mami, have a class, okay? Do you see this class? The Laplace Transform problem set that I gave you, which is a group assignment. Do you see this? Okay, so you can see it. Now, you have this one. I think you can process this. Which part here? So we will use the 15 minutes here time. Which part here in the set of things that you are to take the Laplace transform of that you have a problem understanding? You get your water, Juliana, there. Did you check this as suggested to you? Which part or all of you knows what to do or how to go about answering the 10 items here in part 1? F for me, miss. Okay, Aliana. F for me, letter, that would be letter F to J, L. F to J, L. Okay, Okay, so I have here comments like F to J. Okay, F to J. Okay, I'll give you an example for F because F to J are to be treated in the same manner. So I'll annotate here. Okay, F, I'll give a sample for F. It's the same as the pulse class. The treatment is the same as the pulse which I gave to you a while ago. You first convert this particular form of the function in this form wherein you have the function of t is equal to, so you copy the first value that it assumes it's 1. I will not write it anymore. And you could see the interval here 0 to 2. So you're right. Since it's 1, I will simply write here u of t minus 0 minus u of t minus 2. So for you to understand better, pwede man butangan mo gid 1 because 1 seems to be the value here. Well, where am I getting the 0 and the 2? It came from the interval that is written here. Then you add to it, the second value the function assumes. So it's t squared minus 4t plus 4. Okay, you have to place a parenthesis and it has to be multiplied to, you see this one is just 1, so it's u of t minus 2. Okay? So the treatment is the same as that of the past. What you do next is you distribute the function value to this u of the expressions like that. This one will only be multiplied to the only u of the expression. So you will have, I will simplify now u of t, and that one is, you see this one is a u of t minus 2. So u of t minus 2. And this one, this entire thing will be multiplied to u of t minus 2. So it's a plus, so plus t squared minus 4t plus 4 u of t minus 2. Okay, so far I hope you can still follow through. You see this u, you see this u of t minus 2 and this u of t minus 2 here. It's like you're going to view this as one entity as if it's just a y or an x or an a. So I could see that in my second term and in my third term, I have a common factor which is u of t minus 2. So I'd like to simplify it. So when I simplify, I write u of t. And this one, since it's a multiplier of the two, and these are the factors which need to be combined, I will copy this first because that's positive. So I will write here t squared minus 4t. Now I will stop because this is a plus 4 and this is understood to be a minus 1. So a 4 minus 1 would be a 3. So I'll place here a 3. Then I affix u of t minus 2. It's like I have combined terms 2 and 3 into this. Do you get it? Now, after you're done with combining or simplifying, because whenever you see unit step expression in your function of t, which are similar, you combine them. That way, you will not have difficulty later on in performing Laplace transformation. Now, this one is so easy to transform because the Laplace of the unit step function is simply 1 over s. Well, this one will use property number that was 7, the time translation of the function. Because you have here a u of the expression which is being multiplied to your f of t. Prior to taking the Laplace transform of this entire expression, all the t's here, inilang nga t, kag ini nga t, will be shifted by adding to it the value of this particular constant 2 in here. What do you mean, miss? If this happens to be a 1, all the t's here will be changed to t plus 1, and this also t plus 1. If this is a 10, this will be a t plus 10. This will also be a t plus 10. So to illustrate how it's done, so I'll change this one to, if I will determine now the Laplace transform of this function, automatically this one would be a 1 over s. while this one will be a 3-step procedure. So the first procedure that you will do is, so I'll just place it in here and we will process this. Your function needs to be changed to t plus 2 squared minus 4 times t plus 2 plus 3. I did not change the constant because it's a constant. It doesn't have any t. I will only translate the t. That is why it's called time translation. Then you need to expand this. So when you expand, this will be a t squared. The middle term here will be a 4t, and you have a minus 4t here, so they will cancel each other. This one, when squared, will be a 4 minus an 8 here. So you will have a minus 4 plus 3. So this will be a minus 1. Again, so if you expand this, a t squared for this one, the middle term is 40 minus 40. So that would be now 0. And you have a 4 here minus an 8. So that would be a minus 4 plus 3. So that would be a minus 1. Telling you that this entire thing is just a t squared minus 1. So what will happen to this function of t now? This is the one that you will perform Laplace transformation. So step 2, you perform Laplace transformation on the time translated function, not on the original function. So if you perform Laplace transform to this, your answer will be a 2 factorial over an s cubed for the t squared, and this one would be a 1 over s. Now, you cannot cancel this 1 over s and this 1 over s. Why? Because this one, the third step to this is you affix, you account for the time translation that happened here. How? So based on property number 7, it's an e raised to minus 2s. So first thing, translate all the t's using the constant here. So that would be t plus whatever is the constant here. Then transform the resulting time translated function of t. So this is the transformation. Third step is you affix, simply automatic class, you affix e raised to minus 2s. So this is now the answer to this. That would be the same procedure that you will use for the until letter J. Okay? Now, let me check what's on the chat box. 2 minutes. This letter L sa akin. Starting with F, miss. May over S pa na guro sa may... Ay! Okay. I keep on. Joshua, this one does not have an S anymore. This does not have an 1 over S anymore because it's already accounted for in here. Your Laplace transform for the function is this, and it's this already, and we just multiply it with e raised to minus 2s. A while ago, it has an over s because it's understood that your function there, the magnitude of the function is 1, so the Laplace transform of that is 1 over s. So that is why I have an s there below. But if you do this, the 3-step rule in which you first process the time translation of the function like this, and then get its transform, you simply affix the e raised to minus as or e raised to minus capital Ts to whatever is the Laplace transform of the function. Okay? Hindi siya miss mag-negative. Dali lang, isa-isahon ko lang ha. Starting with F, miss. What do you mean, Mika, with starting with F, miss? Okay, starting with F, there is a problem set. So that's how you're going to process it. Ang asta sa J, amo na siya ang pag-process. Hindi, miss, mag-negative 2s, miss, sa sulod sang bracket. Dali lang. Hindi siya mag-negative 2s sa sulod sang bracket because amo na ni imo function subongo. E squared minus 2. So you're going to get the Laplace transform of that. So it should be negative 1 over s. Okay. So you're going to do GHIJ in the same manner as we have done, as I've outlined it here on F. Okay? Any question? It's 10:30. As for the inverse Laplace, you need to use method of partial fractions here. Would you know how to process C and D, which has an E? It's the opposite of this one. And it's also a three-step procedure. The C and the second term of the D in here, because the first term can be inverted right away, but the second, in terms of how you approach it, will be similar to C. Okay, I will clear now. And let me just borrow one more minute. Okay, the transform of a solution to a certain differential equation is given by this. Determine the solution of the differential equation. It's just like inverting this class. Another way of asking for the solution of the Laplace transform of a DE is by inversion of its Laplace transform. That would already be that would already represent the solution of your DE. And you have the DE here, so you know how to process that. And find the Laplace transform of this and find the solution y of t by inverting. Okay, 4 and 5 is just the processing of a differential equation. You have any concerns here, so that later on during your dry lab, you can do this in your 3-hour dry lab based on the groupings that I have asked you to submit. I think, let me check if I have already placed that you will do group yourselves. Okay, I already placed it in here. So your submission, just like in the previous courses under mid-then class, will be based on your groupings. Modules. Do you still have concerns here? It's 3 minutes, Iha. Wait lang. Isa may 1D, pag 1E is ano na siya ang 7 kag 3 sa may U. Wait, let me check. 1B. Yes, Juliana.
When I was working with it, I found something that's from about the water.
What's in there?
It's the evolution of it.
Right, na siya sa water.
Yeah.
So you change it, you give it to Aya, and you change her water bottle.
That's why I think it's in here.
You change it. Wait, I was able to read. Miss, sa may 1D kag 1E. 1D and 1E. 1D and 1E. Okay. It's a good question, actually. This is how it's represented in other books, class. Whenever you see a subscript in 7 or a subscript here of 3 or any subscript for the U, ang iya represents is that your T here is to be shifted in that manner. So this is to be actually interpreted as U of T minus 7. This is U of T minus 3. Thank you for asking that, because other books, they don't write U of T minus a constant, but they use that constant to be, or they use the subscript to the U as a representation of that particular constant.
You have to do this. That means it's already time.
Okay. Okay, get your water. Let me check.
Oh,
Wait, class, something is wrong with my mouse. What happened to it? Okay, thank you. You're welcome. Some more questions? So if there aren't any questions, class, I leave you the 3 hours tonight to finish everything here. Anyway, you have grouped yourselves, divide the load among the members of the group, and then submit the submission by 8:30 because it will close by 8:30. Your first quiz will be given on Thursday during our 1 hour asynchronous meeting. Anyway, it's really asynchronous and you have nothing there on that particular time. So that would be the quiz, the first quiz for Laplace transformation. Unless otherwise, there are things that you are required to do on that said time, which I do not know. But actually, your other teachers know how your schedules are plotted, so there won't be any task during that particular time which is set for process control. Do you have any questions? Miss Laplace lang gid, wala inverse. Okay, Jess, kinahanglan tagid mag-perform inverse Laplace kay hindi ta matapos ang solutions ang DE kung wala taga-invert. So you might as well review both for Laplace and inverse Laplace. Miss, hindi na sa 31 ang deadline ka problem set. Okay. Let me check. So if I will place the deadline on the 31, you are still going to do it later. Let me check. Ano yung butang ko nga date? Check ko. Okay. I place it on the 31. Sige. You work on it tonight. Starting working on it tonight since it's so many. But you will submit it on the 31. Your quiz will be on Thursday. Last week, I thought Miss na-move na ang quiz. Aliana. You will move the quiz last week. Also,
Last week, Miss, pag-meet, Miss, naghambal si Joshua, bala Miss nga, Miss, wag kami may nadumduman, Miss, kay do wala, bala namon, napadalman sang pag-advance math namon, Miss. Do ang table lang gito, Miss, ang nahatag, bala samon, Miss, wala kami sang unit, step, something, Miss.
Sige. So, we'll move your quiz on Tuesday next week. That would be on August 31. But is it okay that I will ask the submission of the problem set on the asynchronous time because you have already a lot of time and you will not be doing anything for the next 4 hours? Sige, so you will submit the problem set. I will change the deadline of the problem set to August 26. So that you will maximize the 4 hours remaining for process control because I don't want you to be idle and not do anything. And on Tuesday next week in our synchronous meeting, you will have your quiz. Okay? Now, if I can record ahead, which you can listen during the dry lab for the next topic, I will record ahead. That way we will not waste the other 3 hours in the dry lab next week. Because if I don't do lecture, then you won't do anything. What can you do on the dry lab next week if I will not have any lecture? So I need to do lecture. That way you will have something to listen to and do during the dry lab schedule, which is 5:30 to 8:30 next week. Would that be okay to everybody? Your problem set will be due on Thursday instead because you will have nothing to do for the next 4 hours. And then your quiz will be given on Tuesday during the synchronous meeting. That's August 31. And I will post a recording for you to listen for in your dry lab, and in the next probably last hour you will do something that would be on Tuesday next week. That way we maximize the use of your time, unless otherwise there will be some other problems that will be presented here now. Is our scheduling okay? So I can update what's in your canvas now. So can you give me a reaction or anything? Yes, Miara. No reaction. Is the schedule, the new schedule that I gave, okay to everybody? Okay. Sige, sige. So I will have it now edited. That way, everybody will be posted right away or be updated as well in terms of your scheduling. Okay, bye for now, class. Thank you. I have already used up 10 minutes of your time. We'll see each other next week during your quiz. Bye.
Bye, Miss.
Bye-bye.
Bye, Miss.
Bye.